Even our own sun is powered by this process, so without it, we wouldn't exist. This process occurs when two or more atomic nuclei join together to form a single, heavier nucleus, and this releases a huge amount of energy. But triggering and sustaining this type of reaction is tricky. And as of right now, the most advanced fusion reactors only last for a few seconds. So in order to produce fission, you need to consider three important factors: plasma particle density, confinement time, and reaching a high enough temperature. These variables have been very difficult to master, and we have always heard that fusion is just 30 years away. But quite a few companies are coming out with their own radical design, and it's very probable that we'll see a nuclear fusion reactor providing power to the grid in the near-term future. So let's take a look at some of the front-running methods which will create this elusive process known as fusion. The first method is magnetic confinement fusion, and we are going to primarily focus on the tokamak design. One of the front-running projects is called the ITER, and it's a very expensive, multinational government project. It utilizes magnetic fields to confine plasma and initiate fusion. Now, the amount of fusion energy this type of reactor can output is highly dependent on how big the core is, and there are conflicting estimates on whether the ITER will actually produce a net energy gain. Regardless, it's only going to run for a few minutes at a time, so if we only stuck to this one project, fusion really is another 30 years away. Ultimately, the ITR is not perfected, it's very difficult to replicate, and it has cost billions of dollars. Nevertheless, it's going to help us understand the process of fusion a little bit better. This also leads us into a more advanced and refined magnetic confinement reactor called the stellarator. Now, this weird-looking reactor produces high-density plasma that is more symmetrical and stable when compared to tokamak's design. It features 70 superconducting coils in a twisting shape, which creates a magnetic field that prevents plasma from colliding with its walls. Now, theoretically, this would align the plasma better than the tokamak reactor, and it may be able to run continuously, we just don't know yet. Germany has actually built one of the largest stellarators out there, and it's called the Wendelstein 7X. It can produce plasma temperatures of around 20 million degrees at over 100 seconds. The 7X is also still being upgraded for better cooling, and ultimately it could run for 30 minutes by next year. In my opinion, it's definitely a step up from the ITER, but it's still a pretty complex design, and it doesn't output power to the grid continuously. This also leads us into the next process, which is called magnetized targeted fusion. This method is a little bit similar to magnetic confinement, and it utilizes magnetic fields to confine plasma, but a secondary method is then used to compress the plasma in order to produce fusion. General Fusion is one of the front-running companies already utilizing this method. Magnetically confined plasma is injected into the core, and then an array of pistons compress the plasma to fusion conditions. The heat is then captured in the liquid metal, and this is used to generate electricity via a turbine. They have just received funding for a demo plant, so they are definitely worth following. Now, there are a couple of other methods which actually contain plasma. One of them being National Ignition Facility, which is trying to achieve fusion utilizing 192 lasers. Even though it has set record high temperatures, it has not achieved self-sustained fusion, and the program has ran into the billions of dollars, so I don't really like this one. Another project is the Los Alamos National Laboratory, which is utilizing plasma guns instead of pistons to compress the plasma. Just keep in mind that these are research projects, and we definitely don't know if these reactors are going to produce fusion. There's also quite a bit of research looking at Z-pinch technology, which uses electrical current in the plasma to generate a magnetic field that compresses it. Now, I know that's a little bit complicated, but if you can imagine particles in the plasma acting like current-carrying wires that are being pulled towards each other, and this would allow the particles to be compressed enough to start fusion. Now, the infamous Z machine seems to suggest that we can create fusion conditions using high electric discharges. So there definitely needs to be more research in this field, but it's still going to take quite a few breakthroughs. Now we look at another method called field reversed configuration. This is one of my favorite methods because it kind of acts like a real engine. It contains plasma in a magnetic field by inducing a toroidal electric current inside a cylinder-shaped structure. Helion Energy is making one of these devices, and it is far smaller than any other type of reactor. It utilizes pulsed magnetic fields, and it accelerates the plasma at over 1 million miles per hour. The emerged plasma is compressed even more, and fusion occurs, thus providing power to operate the next fusion cycle. The company plans to build a commercial plant within 6 years, which would provide over 50 megawatts of power. TAE Technologies has also built their own machine, which can hold plasma for long periods of time. They also plan to construct their final prototype within a few years. So whether it comes from TAE or Helion, I do think this is one of the most scalable reactors, and it's going to be very exciting to see whether or not they can actually pull this off. Now I'm going to cover pretty far out alternative methods, and you have to be a little bit skeptical when people are claiming to achieve high energy reactions, but the most well-known method is obviously cold fusion, and this stems decades back to the Pons and Fleischmann claims. It is still being researched by several companies including Google and Mitsubishi Heavy Industries. I'm still on the fence with this concept and I'm not sure what to believe with these claims, but anyways, I still think it's a good thing to research just in case that we're missing something that we didn't understand before. And obviously I'll end this video making everyone mad at me, but I'm going to talk about Brilliant Power and their interesting project. Now supposedly Dr. Mills has stated that he's created this reaction which causes hydrogen to go lower than ground state. Any educated person will quickly point out that the Bohr model of hydrogen is based on the assumption that electrons travel in specific shells or orbits around the nucleus. And we can calculate the energies for an electron in the shell, so it's impossible to have a lower than ground state. Dr. Mills argues that there is no such thing as quantum mechanics, entanglements, or relativity for that matter, and that the only laws of nature are Newton's mechanics and Maxwell's equations. So he constructed a new model based on classical physics of the atom, and stated that the hydrogen atom can exist below the negative 13.6 eV energy state. Now I'm not sure if this model is correct, but I think it's a good thing that graduates with peer-reviewed journals like Dr. Mills are challenging conventional physics, because we really need that right now. And physics theory has been stagnated for a long time, mostly to do with institutional funding, but that's for another video. Regardless, I'm not saying that this reactor is 100% what it claims to be, but there is a high temperature reaction going on, and it's going to be really interesting to see what they can develop. People are probably asking, well, why don't you talk about Sapphire Project if you talk about these other crazy projects? Well, the truth is that I don't really think the Sapphire Project is what they're claiming it to be. And I have no idea what kind of plasma temperatures they are achieving with an anoid in a vacuum tube. Once again, this goes back to the fusion requirements, and we need high temperature plasma. So ultimately, this team has to provide more data, and hopefully it's not a hoax and drawing in a lot of money. As a conclusion, we looked at 4 important developments in relation to fusion. The first is magnetic confinement, which is still problematic because the plasma cannot be confined for long periods of time. This has led into more advanced designs, including the stellarator, which could possibly run for long durations, but there are no reactors which supply power to the grid as of yet. Then there is magnetized targeted fusion, which compresses the plasma, but it's still at an experimental phase. There's also field reverse configuration, which collides plasma at high velocities, but that is also at an experimental phase. Obviously, we will always have outliers, including inertial confinement and Z pinching, but these are still far away from producing a reactor which can provide power. I also mentioned some other intriguing topics, including cold fusion and hydrino theory, which we should be skeptical about, but I think it's a good thing to have an open mind about possible undiscovered physics.